Hello, folks. Greetings. Today, I am creating a new video on a little bit of acoustical calculations. Now, I'm doing this for my friend, but for those who are interested in learning a little bit of statistics and calculus and stuff like that, it is still useful. So, let me jump into the concepts, and I'm trying to solve just one problem here, and maybe in future videos I can add more. I can solve more problems. Okay, so in acoustics or acoustical engineering, whatever you want to call it as, there's this concept of Leq and Laeq, right? We just need to want to understand what this means. Okay, now I think it stands for level. um, so it's kind of like, think about it as noise level or sound level, right? So this Leq and Laeq seems to be a parameter that kind of describes the noise level or the sound level, right? um, and it's a very good measure. It is actually a statistical measure. It's a measure where it just represents one value, even though your noise level or sound level may be fluctuating over time, right? So, and basically, if you take the Leq, which is just the sound level, they are what they're doing is they're doing the root mean square um, average, right? It's an RMS average. So, in statistics, what this means is that you sum them up, you sum the squares, right? You sum the squares, and then you take the average of that and then find the root, square root of it. Okay, it's a bit more accurate than a regular mean, right? A regular mean may not include some of those outliers. If you do a root mean square average, that is a little bit better. Okay, now the LAQ is one level better because it uses basically a weighted value. Okay, what is a weighted value? It's just a fancy name for weighted average. Okay, so because your noise levels, your noise frequency, there are various frequency of the noise, right? But for the human ear, so if you analyze with the particular instrument that records sound waves, it will record all the different frequencies, right? But our ear can only sense certain frequencies it cannot sense. And when it senses those frequencies, you tend to hear things that is louder than what is measured in an instrument. Okay, so that is why you add some weight for the audible frequencies, and then what happens is that's the weighted average. Okay, so usually today, even the audio equipment calculates that weighted average and then gives you some values. Okay, so these are all concepts that you got to understand if you want to solve the problem, that the kind of problem that we are going to look at in the next slide. Let's go to the next one. So here's your problem. Okay, a noise survey is carried out in a factory, and the A weighted sound pressure level is monitored from 9 o'clock until 1700 hours, which is 5 o'clock. It is found to be a constant 82 decibels. dB stands for decibels, except for during the lunch break, which lasts from basically 12:30 p.m. to 1:30 p.m., an hour. Okay, when the machines are turned off and the level falls to 55 decibels. So it used to be 82 decibels when the factory is running, but when during the break time it's 55 decibels. Calculate LAQ of 8, which means that an equivalent of 8 hour weighted, A weighted equivalent pressure level, sound pressure level. Okay. The 8 hour equivalent continuous A weighted sound pressure level to three significant figures. Okay. So, how do you do that? So, basically, what you will actually have to do is you will have to, as I told you, that you got to find the um, mean square root, okay, of these various sound that you calculate. Okay, so here is a fancy formula. It looks fancy, but don't get, you know, don't get what do you call looking at this formula and say that, oh, what does this mean? Okay, so here is the thing, and I should have explained this in the previous slide itself. So when you take a linear scale and calculate certain things, okay, linear scale means just use regular numbers. Okay, when you do that, what happens is that when you look at that picture, when you look at that number, it looks much bigger or smaller than what it's supposed to be. Okay, whereas if you take a logarithmic scale, a linear scale is like that. A logarithmic scale kind of makes your number a little bit more summarized. Okay, so you're purely focusing on um, values in a way that the negligible things, the smaller things, are just out of it. That means that your number doesn't have a lot of noise. That's what it means, right? So that's why that LAEQ is calculated in the logarithmic scale. Okay, so you're doing a logarithmic scale, and the root mean square, because you doing a logarithmic scale, you are turning on your logarithmic number inside the integral. So you see that there is an integral there, right? So there is an integral from 0 to t, which is time, total time. So because you're using logarithmic scale outside, you're turning on a linear scale, you're making it a little bit upside down. That's what the 10th power L A of t by 10 dt means. Okay. Now, when you're trying to do this kind of calculation, obviously it's advanced engineering. So, therefore, to solve this problem, you got to have some fundamental understanding of integral calculus, fundamental understanding of statistics, and some basic algebra. Okay. But I'll try to be as clear as possible so that, okay, if you can brush up those concepts, it'll be nice. So if you look at this formula, what you need to understand is when you say integral 0 to t, it means that, see, when you have continuous curve, when you have a curve, or when you are recording values and you're making a graph and the curve is continuous, then in order for you to get an idea of the value of that curve, the the area of that curve, basically, because you want to get all those values, you got to make a sum, right? Statistically, to get a sum of all of those things in a continuous curve, because in the curve, all the points within that curve is part of your statistics. You understand? So, in order to get all those points, what do? You a simple mathematical tool that you have is integral calculus. That's all it is. Okay. So, and then you have an equation, and the equation here is the the sound level for a particular time. Got it? So you're integrating all the sound levels of a particular time interval and then dividing it by the total time. Okay. And that's what this formula is about. So I'm saying all these things so that you don't have to memorize the formula. It's basically 10 into log base 10, okay, logarithm base 10, 1 by t And you literally can, for our this particular problem, instead of putting integral 0 to t, you could have put a weighted average, a sigma weighted average for statistics from 0 to t. Okay, and I'll tell you what that sigma means. Anyway, so that is the formula. Okay, so now let's break it down. Then you I think you'll get a better understanding. So we have, uh, the timing that was given to us is like the employees are working 3.5 hours, 9 to 12:30 p.m., 9 a.m. to 12:30 p.m. Then they get a 1 hour break. That is 12:30 p.m. to 1:30 p.m. And then from 1:30 p.m. they are working until 5 p.m. Okay. So you have 3.5 hours where the sound level is 82 decibels, 1 hour 55 decibels, then again 3.5 hours 82 decibels. Okay, and the total duration is 8 hours. Okay, so and then the other thing is that in order for you to calculate this, because we are using a logarithmic scale, you got to convert everything to seconds. Okay, because the formula applies for seconds basically. So what we do is we take the 3.5 hours, and that is 12,600 seconds. Take that 1 hour, 3600 seconds, and then 12,600 seconds again. Okay. Now, so we got to calculate the LAEQ of 8 hours. That means that it is 1 by t integral of the 10 power 82 by 10, then the integral of 10 power 55 by 10, then again integral 82 by 10. And you're actually showing the integration goes with from what time to what time, right? From 0 to 12,600 seconds, that from 12,600 seconds to 16,200 seconds, then from 16,200 seconds to 28,800 seconds. So that's what that integral symbol comes up to. And the nice thing about integration is because these are constants, okay, the value inside is not a variable, it's a constant. Then the easiest thing you can do is you multiply that whatever that range is with that number directly. Okay, so the range, the first integral is 12,600. The second integral is 16,200 minus 12,600, right? So that will come to 3,600, I think. And then again 16,200 to 28,800, which will be again 12,600. Okay, let me go down to, so you see that, so we took away the integral symbol because it's a constant, and therefore now we literally we all we are doing is doing a little bit of a weighted average for the time, right? So it's 12,600 multiplied by 10 to the power of 82 by 10 plus 3,600 10 to the power of 55 by 10, and then 12,600 multiplied by 10 to the power of 82 by 10 divided by 28,800. So this is all in seconds. Okay. Now, one of the things that you can do is, and of course, I've tried to type all these things, it took a long time. But what you could do is that you could just use a simple scientific calculator, and all these things can be calculated directly, right? Anyway, sometimes people ask, "Hey, show us the steps," so that's why I just put that here. So now I'm taking the terms inside the logarithm, right? Which is one is the 10 to the power of 82 by 10 is 10 to the power of 8.2. That, if I use my scientific calculator, it comes to 1.5849 10 to the power of 8. Then 10 to the power of 5.5, that comes to 3.1623 to the 10 to the power of 5. Okay. So in your scientific calculator, maybe a little bit small differences may be there, but it will be approximately that value. Now, what I do is that now, since I calculated the 10 to the powers, then I multiply that. The inner expression is what I'm trying to do. And that goes on into those steps. And if you put those values, keep multiplying, you get to 3.99475 multiplied by 10 to the power of 12. Okay, then of course all of that you got to divide it by 28 28,800. You get some value, and then take the algorithm, the logarithm of that. If you take the logarithm of that, that comes to uh, uh, 10, and multiplied by then multiply by 10, right? So logarithm of that comes to 8.142, and then multiplied by that, so that is 81.4 decibels. Okay, so then you can say that the 8-hour equivalent A weighted sound pressure level, that is LAEQ8, is 81.4 decibels. It's very simple actually. Once you understand the formula, it's quite simple. It's just that you're using all those symbols, so keep that in mind and you're done. Now, once you have this, you can calculate this for various types of configuration, right? Hey, the employees are taking a 1 hour break, then this happens, and then something else happens, and then in between there's a music concert. Whatever that is, you can get all those levels in and put that and compute this. Not rocket science. And another thing I noticed is that this LAEQ um, can be calculated. There are some online calculators that also does this calculation. Where is this really used? It's really used in industrial settings, in household settings, whatever the settings is, hospital settings, right? Where you want to design your building, setup schedule and everything, so that your noise level is at a level that sometimes you have this industrial standard. So you keep that at that level, because higher noise levels does create all kinds of injuries for employees, right? So that's why you calculate this. Now there's another question here that's asked: hey, how long, rounded to multiples of 5 minutes, would the lunch break have to be in order for the LAQA to be less than 80 decibels, assuming the same levels? So you're saying that, hey, the noise is the same, okay? But because there is a lower noise interval, that is the lunchtime, which is 55 um, decibels, is there a way to stretch that time? And so I can get 80 decibels, right? And I think 80 decibels is um, the OSHA uh, mandated number. I think, I'm not sure, right? OSHA in the United States, other countries will be different, right? OSHA is for it's an ergonomic standard that the government sets, right? So they say that, hey, what can you do? How can you stretch the lunch break? How long do you need to stretch the lunch break, so that you get, instead of 81.6 decibels is what we saw, can it be 80 decibels, right? So again, here the formula is, I showed you the integrals and everything. Now we kind of reduce the formula to what we are seeing this formula here. Okay, it's 10 log 10, 1 by 10. You take the first time interval, multiply that 10 to the power of L1 by 10, and you take the second time interval, and then you do 10 to the power of L2 by 10. So that means the total period is t, right? Now you can easily calculate the first the t1 is actually 28,800. Subtract that with whatever the time t2 is, that's the lunch time, right? So you take 2800 28,800 seconds, subtract that with lunchtime. We don't know how long is the lunchtime, because that's what we need to calculate. You get t1. Then t2, you need to solve for t2. That's what this is, right? So t1 is the time at 82 decibels, t2 is the time at 55 decibels, L1 is 82 decibel, L2 is 55 decibel. So same formula, except that we know what is t1, which is total time minus lunch time. We don't know what is t2, okay, which is what we need to calculate. So how do we calculate this? So we the first thing we try to do is we convert that 80 decibels to a linear scale. Okay, remember that we need to use logarithms, right? So instead, if we convert everything to linear scale, then we don't have to use logarithms. So what we are doing is we are doing 10 to the power of 8 by 10, which is 10 to the power of 8 for that 80 decibels, right? So now you take that formula, the formula, because you take the logarithms out. Again, to simplify, if you want to use a scientific calculator, we don't even have to do these kind of calculations, right? We're just simplifying it. But the bottom line is we need to get T2. So as I said, 1 by 28 and 28,800, that's the total time. Then 28,800 minus T2 is the work time. And during the work time, you are dealing with 82 decibels, which we convert that into linear scale, that is 10 to the power of 8.2. Plus T2, we don't know. How long the lunch time, we don't know. But then we are multiplying that by 5.5 decibels, because during the lunchtime, since you're shutting off all the machines, it's only 55 decibels. Okay, so now we keep going on so that we can get T2. So we keep figuring out what is that value, right? So it's 1 by 28800. You can convert that into some value, then so that is multiplied by 10 to the power of 8, then 3.1623 multiplied by 10 to the power of 5. So all these things are there. And now I'm basic algebra, right? I keep going down to the level where at some point it says it's 1.68 something 10 to the power 12 is equal to minus something. Then I just calculate T2. Of course, the minuses becomes positive because the signs are same on both sides. And then you're dividing. Then it says T2 is approximately equal to 106,051.96 seconds. Of course, we want to give some proper value. So we now divide that by 60. We get that many minutes. And then we uh, say that, okay, let me round off for 5 minutes, right? So that gets me to 180 minutes. So that means if you want the decibel level, the average, the Leq, okay, the weighted average of the decimal value to be 80 decibels, then you got to give a 3 hour break, lunch break, to your employees, right? So this is a very good idea. I don't know anybody is going to give 3 hours of a lunch break. um, However, it could be, for example, in a hospital setting or something like that, when somebody is suffering from some hearing disorder, right? So you can calculate, okay, if I can give 3 hours of break, then maybe they only get 80 decibels in their ears, right? Something like that. So you can calculate that. The next one is another question. So the factory manager is saying that, hey, we want to make the factory quieter. The machines are turned off in the lunch. So during the lunch break, I want to do something in order to achieve 80 decibels without extending the lunch break. So what uh, this manager or somebody says is, hey, I don't want to reduce the lunch time, but why is it 55 decibels during the lunchtime? Can I reduce that decibels to less, so that I don't want to give them 3 hours break, but how can we reduce the sound pressure during that time is the question. Okay. Well, we know the rules now, so we can do that, right? So we just say that, okay, for 8 hours, the the time period is 8 hours. T1 is 7 hours. T2 is 1 hour, and what we are desiring is 80 decibels. Okay. So again, you can come up with the formula. It says that, hey, you know what? That's the formula. We know that formula. Now we say that, okay, that has to be 80 decibels. That is 10 to the power of 80 by 10. Again, I'm taking away. So from the logarithmic scale, I'm just making it linear scale. Um, so therefore, the value 80 becomes 10 to the power of 80 by 10. Okay, which is 10 to the power of 8. 10 to the power of 8 is that value, and the lunch break, right? So the 82 decibels plus whatever the decibels you can reduce for the lunch break, right? So you keep going and you keep going and you keep going. At some point, you see that the the left hand side of the equation is, okay, you got to have a negative 1.11.48 or 0.0348 to the power of 10 to the power of 12. Is that negative value is 3600 into 10 to the power of whatever uh, uh, the power is, right? Now obviously, then why this negative value comes into play is basically you cannot find a decibel value. Your decibel value is much much lower. So just by keeping the lunchtime noise low, there is no way you can actually um get to that goal of 80 decibels. That's the finding here. When it is negative, then yeah, there is no way you can do that. Now obviously, the question here asked here is, a so if that's the case, what do you recommend, right? So if you are a consultant, what will you say? The manager is saying, hey, is there a way, can I reduce it to 80 decibels, but I don't want to give a break on the lunchtime or whatever. Then what we need to recommend is that, hey, it's not just the lunchtime noise you need to reduce. You need to reduce the overall, the holistic noise. Okay, why is your company's um, work time is so noisy, right? So the recommendations, and obviously I've just put some recommendations here. Now if you are answering some exam questions or something like that, and you may have to provide them some citation, right? And so I'm just summarizing what's been provided in all the books. Obviously I did some research, right? And the ideas are very very simple. Okay, so when it comes to sound, you can do sound insulation, you can put some sound barriers, and you can do some soundproofing techniques. So which means that, so sound insulation means that you are, uh, see, the sound that is happening in particular area should not escape, should not get out, right? So you can put some sound absorbing materials around, things like that. That will make the sound to not dissipate that much, right? Then you can put sound barriers. You can see that in some places, like if you go on a highway or something, and there are houses nearby the highway, they just put a big sound barrier with sound absorbing material, so that way that the sound does not leak through to the other area, right? So keep the other area a little quieter. Then soundproofing is another technique where, um, like what I'm doing right now is, I spend a lot of time to proof this, to make sure that there's no other noise that happens when this happening. So there are techniques. You can make the equipment quieter. You can put barriers around the equipment. You can put sound absorbing materials on louder equipment, stuff like that, to reduce the sound. Okay, that's obviously you got to do. The other thing you can do is, you could provide some equipment where employees can plug their ears, and then you can also relocate the location of the lunchtime, things like that, to help reduce noise. Thank you very much.